Have you ever looked up and wondered, why is the sky blue? Why isn't it green? Or purple?
Simply wonder.
If you step outside on a clear, sunny afternoon and look up, you will almost always see a bright blue sky. It is such a normal part of life that we rarely stop to ask why it looks that specific color, rather than bright green, a deep purple, or neon orange. To find the answer, we have to start with the source of that light, the sun. When sunlight beams down and hits the ground around you, it appears as plain white light. While it looks like a single thing, that white glow is actually a composite of several different elements working together. Sunlight is a highly colorful mixture of ingredients, bundled together so tightly that they stay hidden from view until they encounter an obstacle. Every color of the rainbow is present in sunlight, traveling together in a single tight bundle. We can see this in action if we look at this photograph of a special piece of glass called a prism. When you shine a beam of white light into it, the crystal disrupts that tight bundle. By bending the light as it passes through, the prism separates the beam, revealing the distinct bands of red, yellow, green, and blue that were traveling there all along. Because the sun is constantly bathing the Earth in all of these colors at once, the blue we see in the sky is simply one specific ingredient of sunlight reaching our eyes. Light energy travels through space in waves, very much like the ripples you see moving across the surface of a pond after you drop a pebble in the water. If we look at these two examples of light waves, we can see the core difference between colors. A color's entire identity is determined by the physical length of its wave. The color red travels as a long, lazy wave, with massive stretched-out strides and peaks spaced very far apart. The color blue, on the other hand, is a short, choppy, and energetic wave, with peaks tightly packed together. Because blue light waves and red light waves are physically different sizes, they interact with obstacles in the real world in completely different ways. Look at this high-altitude view of Earth. That thin, glowing blue band is our atmosphere, a protective blanket of invisible gas molecules wrapping the planet. As the colorful bundle of sunlight hits this giant atmospheric obstacle course, the long, lazy red waves are large enough to simply step over the tiny gas particles. They travel straight down to the ground. But the short, choppy blue waves are the exact right size to hit those tiny gas particles. Instead of stepping over them, the blue waves crash directly into them. This collision causes the blue light to bounce off the particles and violently redirect everywhere. Scientists call this chaotic bouncing action scattering. When you look up and see a blue sky, you are looking at the visual result of millions of these short blue waves scattering off the air, bouncing around the giant pinball machine of our atmosphere. This brings up an interesting question. Why does the sky turn brilliant red or orange when the sun goes down? When the sun drops low on the horizon, its light hits the Earth at a severe angle. To reach your eyes, that light now has to travel through a much thicker, longer slice of the atmosphere. Over this long distance, those energetic blue waves hit so many particles and bounce so many times that they scatter completely away. They are exhausted before they ever reach you. The long red and yellow waves, however, are built to survive this extended obstacle course. They casually step over the extra particles and pass straight through to your eyes. Sunsets appear red because the thick layer of atmosphere acts as a filter. It removes the scattered blue light, leaving only the longest, most resilient waves visible at the end of the day. We can see this filtering effect in extreme conditions, too. If you look at this image of industrial smoke, you can see how human-made elements like pollution or heavy dust act as giant bumpers. They scatter away the blue light so aggressively that the sky turns intensely red even in the middle of the day. A sky's color depends entirely on the specific size and type of particles floating in a planet's atmosphere. Take a look at this photo from the surface of Mars. The Martian atmosphere is very thin and filled with fine dust particles. These particles scatter light differently than our air does, giving Mars an orange or reddish sky during normal daylight. And when the sun sets on Mars, this specific atmospheric mix creates the exact opposite effect as Earth, filtering out the red light and leaving behind a blue-tinted sunset. Light waves physically interact with the gases and particles they pass through. By mapping those collisions, we can decode the vibrant colors of any sky in the universe.
Simply wonder.